Next, we will see work done by friction. So next, we are going to see work done by friction. So for discussing that, we will consider the motion of an object on a rough horizontal surface or rough table. So consider motion of a block on a rough horizontal table. Horizontal table. Okay, so suppose block was here and it was moved like this and it is finally here. Okay, on the table. Okay, so block is moved from position A to position B. This whole thing is in horizontal plane. This whole thing is in horizontal plane. This is not the vertical plane. The diagram is not in vertical plane. It is in horizontal plane. We are looking from top. Okay, so how will the friction act? So we will see how the friction acts. So consider a place here. Suppose this is the place, an object is moving. So what are the forces acting? So there will be a downward force mg and there will be upward force normal. See, this is in horizontal plane, so mg will be into the plane, that is shown by cross, and normal will be upward, so that is outward. And since the object is moving in this direction like this, the friction will be backward, opposite to the displacement. Okay, so friction acts opposite to displacement, and since it is sliding, the value of friction we can write as mu times normal, if mu is the coefficient of friction. So m is mass, mu is coefficient of friction. Okay, so this is the value of friction. Now if you want to write work by friction, so the friction is constant or variable. So you can see that although the value of friction, the magnitude of friction is constant, but its direction is changing. So we cannot consider it as a constant because the direction of friction is changing. Why changing? Because you can see at this place the direction is opposite to this point, but here if you see the direction will be like this. Means direction is always opposite to the velocity. Okay, so friction direction is changing all the moment, so friction is not constant. So we can write, we can consider it as a variable. So we can write f dot ds integration. We can write like this, and f and displacement are exactly in opposite direction, so we can write it as f ds cos 180 degree. Okay, or we can write minus fds. Okay, so now we have converted this vector thing into the magnitude only, and after this, if you see, after this the force is now in magnitude. These two now are magnitude only. After taking dot products, this quantity are what? Magnitude only. So f is now magnitude only, so magnitude is constant. Now we can put the value of friction. So value of friction was mu mg. Normal was equal to mg from mu mg. So now we can put the value of friction. So that will be mu mg into ds. Okay. Now the work done we can write as what a constant. So mu is constant, m is constant, g is constant. So minus mu mg into ds. This one we can write. And what is ds here? So ds was the magnitude of displacement. So if you integrate this ds, if you add this ds, the ds will give the total distance traveled or the path length, because this is magnitude, this is not displacement. So we will write like this, mu mg into s, where s is distance traveled, not the distance, not the displacement, distance traveled. This is distance traveled, not displacement. So, or the same thing we can write the work as, we can write as the magnitude of friction into displacement. Okay, sorry, into distance traveled. No displacement is there, only we have distance here. So what we can conclude from this situation, first thing we can conclude here is the work done by friction in this case is dependent on path. Why it is path? Because it is distance traveled. The distance traveled is actually path length. Okay, so work by friction is dependent on path, depends on path. Okay, so even if a particle moves on table and comes back to the same position, so displacement will be zero, but distance will not be zero. So the work done will be what? The work done will not be zero. Okay, and in this case the work done is negative, but the friction does not have always negative work done, but in most of the cases friction gives negative work done, as it is shown in this case. So work done by friction is negative in this case, but not necessarily always. So I'm writing it: work done by friction is negative here, but it is not negative in all cases. Okay, we will see in what cases it is positive or zero, but it is not negative in all cases. Okay, so this is the work done by friction, and this is negative work done. Okay, in this case it is negative work done. So this is the learning from the work done by friction. So now we will also see some other examples like work done by friction when we have positive work done. Okay, so we will see those examples also. So next we will see the another example of work done by friction. So for friction, if we have, suppose one object is kept over another object, okay, and they're on the table, and this object is getting pulled, lower object is getting pulled. Okay, if there is a friction here, then F will act here, and the friction will act in forward direction. Okay, so if you see the work, this is A and this is B. So work by friction on A. On A, the friction is in backward direction, movement is in forward direction. So displacement is in forward. Okay, so friction is backward, displacement is forward. So work done by friction is how much? Positive for A. So friction, opposite. Friction is backward. So F into S. So this is backward and this is forward. So we will write cos theta, so that we have to write minus Fs, so that is negative. Okay, on A. Now if you see for B, for B the friction is forward and displacement is also forward. So friction is forward and displacement is also forward. So work done by friction on B will be F into S cos 0. So it will be Fs, that is positive. Friction and displacement both are along same direction, so work done will be positive. So this is forward and this is also forward, both are forward. Okay, so the work done will be positive. So you can see the work done by friction is positive in this case on B. So you can have the work done by friction as positive also. Okay, there are some other cases in which work done by friction is zero as well. So in what cases you have zero? So there are examples. Suppose a car is moving on a circular road. We have a circular road and a car is moving on a circular road. So the centripetal force is provided by friction, but the displacement is in this direction, and the centripetal force is towards the center. So centripetal force is towards center and displacement is like this. So they are perpendicular. Okay, so this Fc is coming from friction actually. This Fc is the centripetal force is coming from friction. So work done by friction in this case is how much? Since F is perpendicular to S, the work done by friction is 0. Okay. So in this way, we can see the work done by friction can have any value, positive, negative, or 0. But generally, it is negative. So that we saw in the last case. Generally, the work done by friction is negative, but you can have any value.